Thank you for joining us for an in-depth technical demonstration of Lozen for revolutionary data access. My name is Jeannie Glass, and I'm CEO at VirtualZ Computing, and with me is Vince Ray, our Chief Technology Officer. There are thousands of packaged applications like Tableau and others running in the cloud and on distributed platforms that require access to data residing on IBM Z, where more than 80% of the world's business critical data is stored. Today, customers spend millions of dollars, create and maintain custom code, and expend 5 to up to 20% of their high value mainframe capacity on legacy data access methods such as ETL, FTP, and change data capture, and lift and shift data from their mainframe to their cloud and distributed platforms to run their business. Despite these costly and time consuming processes, customers have to transfer terabytes of read only, static, and out of sync copies of their data from their mainframe on the left of this illustration to their cloud and distributed platforms on the right. In addition to existing packaged applications on the right, this data access problem is compounding as the number of application migration projects increase, creating more demand for more access to more business data residing on IBM Z. Oftentimes, after several years and millions of dollars have been spent, customers still don't have an early migration success they can point to. And that's where Lozen comes in. In addition to real time, read write, data access by packaged applications, Lozen delivers unprecedented benefits to application migration projects by allowing you to migrate just your applications and leave your data securely where it is. With Lozen, your data stays on IBM Z. You maintain real time read write access by applications that have been migrated to the cloud and distributed platforms, and the data dependencies for those applications remaining on Z stay intact as well. And now I'll turn it over to Vince for an in depth technical deep dive into how Lozen works.
My name is Vince Ray. I'm Chief Technology Officer and one of the founders at VirtualZ Computing. Today we're going to have a look at Lozen. Lozen is our product that allows mainframe data of many different types to be shared with just about any application, whether it's a ported COBOL program running in the cloud or really just about anything else, cloud or on-prem. Now this is the infrastructure that's behind our demo today. On the left we start with a standard ZOS mainframe. The mainframe is running all the typical things you'd find on the mainframe. And in this case specifically, we're also running the Lozen server on the ZOS system. Also on the mainframe, as you see in the top right, there are a bunch of different types of data sets that we want to expose through Lozen, everything from VSAM files, sequential QSAM files, even Unix services file systems. We'll see each of those in the demo as we go. They all behave roughly the same way, and that's actually the beauty of Lozen. You can get to just about any of your mainframe data through it. Now, the mainframe is connected to the client system we're going to use over nothing more than a TCP/IP network. There's no special hardware here. There's no special software here. It's just an open network. On the client side, we're using Linux. We'll have some examples also in a Windows environment. But typically, at least the first part of the demo will focus on Linux system. It's an x86 Intel server, and in our case, we're going to look at a system in our labs and also an example in the cloud. All right, so let's start by actually looking at what's going on the mainframe side of Lozen. So what I've done here is I've just logged into my mainframe using SSH client. You can do what I'm about to do any number of ways from TSO, ISPF, really anything that can issue Unix services commands could be used here. I'm using SSH because it's convenient for us and it fits our network. So when you install the Lozen software, you'll end up with a directory in your Unix services environment with this type of structure. Let me just display this subdirectories. A lot of things like the README files and so forth you'd probably expect. But let me spend a few moments on each of the others. The clients directory would be any software from us that you would need on other platforms. If we look at what we include in there, today it's really three things. It's the Microfocus integration that we've built. It's a Mule ESB integration that we built, and an OpenAPI connector that allows you to plug Lozen into pretty much any technology that's based on OpenAPI. We'll see the Microfocus integration in action later in the demo. But the important point is, except for these three clients, you generally don't need client-side software from us. Lozen works fine with just the NFS client that comes built into most operating systems. You'll see examples of that as we go. So beyond that, the key configuration data is in the conf directory. If we look at the files in there, most of the things that you see here are really all about communicating to Lozen what parts of your ZOS inventory of data sets that you want to be exposed to the network. It's not an all or nothing thing. You can have certain VSAM files and QSAM files, and whatever your needs are, you can have exposed, and then you can also group them into different mount points and so forth. So different clients, maybe with different privilege levels, get to see different subsets of your ZOS data. It's not, as I said, it's not a all or nothing approach. It's an approach where you get to decide these are the specific data sets that I want to expose. And then really going a step beyond that, in our default configuration, we use the data directory that you see above to control the individual ZOS data sets that are going to be visible to network clients. It'd probably help if I show that. So we can see just some of the test things that we've done. And what you notice in the syntax here is that most of these files aren't like conventional files. They're what IBM refers to as external links. What that means is there's an object in the Unix services file system that really just serves as a placeholder. It's a name, and in our case, it's a name that's friendly to our network clients. Most network clients aren't going to know about things like data set names and PDSs with member names and all of that kind of stuff. So instead, we expose names that are going to be friendly to other systems. But we use the external link to connect those objects to real data sets in the underlying file system. You can see here, just as an example, about 3 lines from the bottom is a file called VSAM KSDS. All of our remote network clients would access through that name, but when they do that, what they're really getting is access to a ZOS dataset called vince.testvsam. And we'll take a look at some of this later on. But these are real, honest-to-goodness, VSAM datasets, QSAM datasets, PDSs, and so forth. So, and also the other thing I'll just quickly point out is we also have multiple mounts here. You see near the top of the display, there's a directory called mount2 that serves as a different mount point that some of your network clients can use. So if I wanted to put things inside of that mount point that would only be visible to a subset of my clients, I can absolutely do that. And let me be clear too, when it comes to security checking, when a remote application actually does open and access a file, doesn't matter what the name, doesn't matter what mount point is, the way we do that integrates with your ZOS security product, whether it's IBM's RACF or Broadcom's ACF2 or Top Secret. Uh, in every case, you get to use the security policies and the features of the security product that you're used to decide who ultimately has access and who doesn't have access, as well as to do things like auditing and so forth. It's a very key part of our design. Returning to the installation directories, just a few other quick things I'll point out. The metadata subdirectory that you can see sort of at the top of the screen is what we use to understand the structure of VSAM files. VSAM files can be very complicated. They can have text fields, they can have binary fields, they can have packed decimal, mainframe style, floating point, all sorts of things that most distributed applications generally aren't going to understand. So we build in a transformation capability that allows the remote client to see the data in a way that's sensible to him. If he wants to see text fields as UTF-8 or ASCII, he can absolutely do that. If he needs to see, mainframe packed decimal fields in some other format, we can do that as well. We can even take it as far as to transform what might be a really complicated VSAM file into, let's say, a CSV file or an XML file or a JSON file. So all of that's driven by files you'd see in the metadata directory, and really all they are is layouts, almost schema definitions, if you want to think of it that way, of the VSAM files that you've got. The good news is that we support extracting schema from things like COBOL copybooks. So if you've got, let's say, a mainframe COBOL application and it's got its file definitions in a copybook of some sort, you can point us to that copybook and we'll figure out what the schema is, store it in the metadata directory, and then all of the remote clients that would connect to us can understand this is the structure of the file, and we can use that to drive transformations. Last thing I'll mention while we're in here is the log directory, and in fact I'll go show you a couple of things in there. When VirtualZ is running, we generally will produce the three files that you see here. There's standard out file would have kind of error messages, startup messages, things that are just generally applicable to the kind of ongoing operation of VirtualZ. The log file, the vzcnfs.log that you see in the display here, that's detailed debugging information. Today we ship the product with debugging information enabled, so if there's any initial question you might have about what we're doing and what we're accessing and how we're doing it, all of the gory details would be in that file. You can probably figure out exactly what's going on from there. Certainly we would recommend that in a production deployment you turn off the debugging so that you would only see exceptional conditions in there. And then the statistics file is a collection of metrics that we maintain while we're up and running. And in fact, I can show an example of that. Normally, the way we would start the Lozen server is just through a command line Lozen command that we provide. And again, there are a lot of ways of doing this. You could do it with JCL. In a production environment, you would probably configure it to automatically start when your ZOS system comes up. I'm going to do it by hand here. So first, in our system, I already started the server before the demo began. So I'm just going to show the status of it. And and this is basically the kind of information that we keep in the stats file that I described before. We can see that our server process is running. We see its process ID. We see things like the network ports that it has open. We see statistics in terms of the license status, and normally the only time you'd see anything different here would be if you're running a trial version or an evaluation copy of our software. No expiration or anything like that. You can see we're running on a ZOS 2.4 system. When we were started, how much memory we're consuming. A significant thing is the zip capture ratio. This is the percentage of the CPU resources that we're using that are being dispatched on a zip engine, so 97%. And I would say that's typical from our testing, is running on the zip, and slightly under 3% would be running general purpose MIPS. You can also see whether you have some of the optional features like Kerberos security or TLS security active. You can see how many mounts were done against each of the mount points. Number of file opens, closes, and how much data is read or written. Below this section, we have some more details about the actual mount points that have been defined. Again, you might see options here about some are read-write, some are read-only, lots of other options that are possible there. And then finally, we have some information about the data sets that we've actually been processing. I'll skip to this one because I called it out before. You can see that we processed a particular VSAM file. You can see when that data set was created and so forth. You can see the actual underlying data set name and all of its attributes, the record length, number of records, all of that, and anything you might want to know. Significantly, it is keyed, so it's a VSAM KSDS. It's a record-oriented file as opposed to something like a Unix services file that might be just a byte stream. It is a VSAM file. It has keys. The keys are starting in location 0, the beginning of the record, and they go 8 bytes long, and so on and so forth. A lot of these details we make available to our network clients, so they're able to connect to the mainframe and understand what they're looking at. They can, a sophisticated application could look at something and say, oh, that's a VSAM KSDS, and I know how big the key needs to be, and all these other attributes are visible to it. And then, finally, we just have a little bit of information about the various internal threads that we're using to service all of our connections. So that's pretty much it. At this point, we have the server itself running. We have it configured with security definitions. We have it configured with data objects to serve to clients. Let's take a minute and take a look at kind of a different part of the puzzle. We'll take a look at one of the VSAM files that we're going to look at from the mainframe's perspective. All right, so what we're going to do now is we're going to take a look at some of the actual VSAM data that we're going to send through the Lozen server, so you can see it in its native form on the ZOS platform. Now, to do this, what I've done is I've just logged into TSO, ISPF, and I'm using IBM's File Manager product because it has the ability to view and edit various types of VSAM files. So what I'm going to do is I'm going to go into edit mode here. And I've set up a very simple VSAM file. You see the name of it there, vince.testksds. When I display the records in this file, you can see it's very simple. There's really just 10 records in this data set. If you look a little more closely, you can see that each record is divided into a key portion and a data portion. The keys exist in the first 8 characters. The data exists in the rest of the record. If we look at just some of the details here, you can see that, yes, it is KSDS, and all the attributes about it. One thing I'll point out here is the share options. In this case, there's just a standard VSAM file that we've defined with share option 3, so we're going to allow it to be shared kind of under application control. So that's at least a subset of the data that we're going to look at today in the demo. It's we can look at all of the other files that we're going to use, but they all pretty much have the same kind of structures. Could be, in this case, it's just a trivial example, but certainly it could be as complicated as you like. Certainly the data can also be other types of VSAM objects. I'm looking at a KSDS here, but it could be a relative record data set. It could be an entry sequence, VSAM sequential file. It could even be things like alternate indexes and so on. So really anything that you can define in VSAM are eligible for processing inside of Lozen. Right, now we're going to look at how we'd actually access some of our mainframe data from a network client. In this case, what I've done is I've just logged into a local Linux server that's here in our labs. It's just running on commodity x86 hardware. It's just a standard Linux distribution. And what I'm going to use to access our mainframe data is nothing more than our Linux system comes with out of the box. And this is a really important point. There's no proprietary APIs from VirtualZ. There's, in fact, no VirtualZ software installed at all on this Linux system that we're going to use. It's just the standard components that come with Linux. So the first thing we're going to do to access our data is we have to establish a connection to the mainframe. That's done with the Linux mount command. So let me bring one of those up here. So I'm gonna issue this command, and what it's basically saying is that I want to create an NFS session to a computer called VZC DAO, and on that computer I want the root directory, and I want it to appear as though that data is stored in a local directory on my system called /mount/uppercase-Z. So let me execute that, and what's going on under the covers here is this is where the Lozen server is understanding who the client is, whether he should have access to this particular mount point. He's applying all of those policies and then creating, think of it as a network session between our client and the mainframe. We can see after the mount, we can see some information about the mount point. I'm just using the df display file systems command to look at that file system we just mounted. And sure enough, after the command completes, I can see that we have a mounted file system on that server that I mentioned, and it's locally mounted at /mount/z. And I can see a few other attributes. In this case, the file system on our mainframe is 2 gig, and it's mostly used, 90% used. So we know that we're connected at this point. We know we're able to process mainframe data at this point. I'm going to do this with a very simple command line example. And I'm going to do exactly what you see here. I'm going to display a file called VSAM KSDS within our mount point. So /mount/z/VSAM KSDS. This is that file that we looked at before in the 3270 session. And I'm not going to specify any kind of transformation or anything. So we're going to get those records in just a pure binary format. And what that means is, typically they're going to be stored in EBCDIC format on a mainframe. So what I'm going to do is I'm not just going to fetch all of those records. I'm also going to run them through the icon utility, and I'm going to ask for them to be transformed from the IBM 1047 code page, which is EBCDIC, to whatever our local system is configured as here, which is UTF-8. And then finally, this last piece is just to make the data fit on my screen a little bit better. What we're doing is we're just inserting new lines every 80 characters so that we see the records the way we expect them to be. So I issue this command, and what's going on is the NFS driver on our Linux system here is communicating to the Lozen server, expressing what it wants, and Lozen is transforming those requests for VSAM KSDS into lower level VSAM access to a particular VSAM dataset and returning us the records as you see them here. And if you remember, this is exactly bit for bit what we looked at with File Manager from mainframe. We fetched exactly the record set we expected to in this case. So an interesting thing here, though, is that my Linux system is fairly current. It has support for NFS 4.1 and 4.2, which are two of the more recent versions of the standard, and they're actually very good at things like caching. If I were to go back and access this data again, the second access to the data didn't require us to transfer any data. All we had to do was communicate to the Lozen server and ask whether any of the data we care about has been changed or not. In this case, it hasn't, so my Linux system here is free to fulfill that access request using data that it's got cached either locally in memory or locally on my disk here. So what that means is if you've got the kind of applications where you're banging away at the same data over and over and over again, what tends to happen is that the first time you reference a particular record, it's brought across the network from the server, but on subsequent accesses, as long as the data doesn't change, it's all satisfied locally out of the cache, which can be many, many, many times faster, especially, in this case, our file is pretty small. But if this were terabytes of data, we would save the need to do massive transfers that way. And the beauty of this is that it's also real time, so that if that data were to change on ZOS, we would just automatically see the cached portions that have changed flushed from the local cache, and we get new copies of the data. That they're always up to date, and there's no way to read anything that's not up to date. So this is the basic model that we use. You reference a file with nothing more than standard operating system things, open, close, read, write. If we were to look at what's inside that cat command, it's just, in this case, it's a C program that's doing nothing more than accessing local file system objects, and we've made it access the mainframe this way. Now we can do some more advanced things. And it follows the same idea. Let me bring up an example of that. Let's get the screen cleared and let's take a look at another example. This looks very similar. We're accessing the same file, but if you notice, we've added an advanced option to the file name. We've said, I don't want to fetch the data for the file. I want to see the metadata of this file. We have many different advanced options. They do everything from search for a record by its key to read a file backwards. There are many things that can be specified there. In this case, I've asked for the file metadata, and you can see just about anything you'd want to know about this file is available to the application here. We can tell that it's EBCDIC. We can tell that it's the data set name of the underlying file. We can tell that it's not just that it's VSAM, but that it's a KSDS and how big the keys are and where inside the record the keys fall. Just about anything that the application might need to know about the file is in the metadata. So if you're writing in a sophisticated application that's trying to, I don't know, deal with a keyed record and it needs to know where within the record the key needs to be placed, it can use metadata for that kind of stuff. We do a lot of this in the Microfocus integration that we're going to look at after this, and you'll see many more examples of using the advanced access to files. So, last thing we'll look at here is, just as the mount command established a session to the mainframe, we can use the unmount command to close that session, and now we're completely disconnected from ZOS in this case. So that's kind of the way everything we do works. Between the mount and the unmount, that defines a session to the mainframe. You can process as many files as you want. You might have single files like we've been looking at here, but you could just as easily have an application that opens 100 files and processes them all concurrently. There's only one mount point in that case. It's very flexible, very easy, and very familiar to other platforms that are accustomed to remote access to data this way. So that's this part of the demo. We'll kind of move ahead and take a look at the Microfocus integration, where we'll see some more kind of lower level access to some VSAM data. So next we're going to look at the Microfocus integration, and the first step is going to be to install the actual software. We package this up with Lozen, so it's in the mainframe distribution. You can download it and run it anywhere that you might need it. So we'll navigate to the directory we downloaded into. We'll run the install command, and when that launches, you'll see it looks very familiar to anyone who's ever installed Windows software. So really it's just going to be a matter of stepping through some of these prompts. You would specify the directory where you want it installed, and then there are really 3 bits of data. You need the host name or IP address that will connect to. By default, this is your mainframe. Number 2, the port number we use, 2049, is the NFS standard, and a path that serves as the mount point. We also package up a DLL that contains a lot of our core capabilities. You would point to that, and then pretty much you're done. The README is really minimal at this point. And now let's go look at the files that we created. You'll see the directory with all of the files. There's 2 important things here. The file handler configuration controls, primarily what files that will service. If you look at the syntax here, it's file names starting with student are mapped to our file handler. And this allows you to have many files, different names, some managed by us, some not managed by us. You can have as many entries as you like in this file, and that's going to control what we actually process inside of the Microfocus environment. You can change this at any time. You can have multiple instances of it if you need to. Now with the actual Microfocus integration installed, let's take a look at the VirtualZ file handler in action using one of the demo programs. So this is the actual demo program we're going to run. It's a Microfocus COBOL program running in their environment, and it shows very, very simple processing. It's using a simple indexed file that's got locations of airports around the world. allows you to enter any two airport codes, and it'll give you the distance between those airports. Interesting to us is it's an indexed file. It's KSDS that we're going to do search by key and all sorts of record-oriented functions. So we can browse through the program, but and you can see the file definitions. You can see the layouts of the records and so forth. This matches what we've set up on our mainframe in the KSDS that we created. So let's run the application. And when it starts, we can see that it's very simple. It lets us type in two airport codes. We'll use London and JFK. Hit enter, and we see the program's computed the distance. In the log file that we maintain, you can also see that we've connected to Lozen. We've fetched a collection of records. We've done exactly what I've described here. So pretty much that ends our demo for today. We've seen a whole variety of things, and definitely appreciate your attention through it. And by all means, don't hesitate to reach out to us if you have more questions.